In a previous video, we talked more about the theory of optical activity. In this video, I'd like to do some examples of calculations on specific rotation and enantiomeric excess. So this is the first of two examples. So for this problem, we're told that when 0.19 grams of cholesterol is dissolved in 3 milliliters of ether and placed in a sample cell that's 20 centimeters in length, the observed rotation at 20 degrees Celsius using the D line of sodium is negative 3.99. And we want to calculate what is the specific rotation of cholesterol. Okay, so this is our equation for specific rotation, where when we put the alpha in brackets, that tells us that it's the specific rotation. The alpha without the brackets is the observed rotation. C is the concentration, and the concentration needs to be in grams per milliliter. And L is the path length, and that needs to be in decimeters. So before we can plug everything into the equation here, we need to do some unit conversions. So we need to use the mass and the volume of the solvent to get the concentration, and we need to get 20 centimeters into decimeters. So to determine the concentration, it's just going to be the mass of the solute divided by the volume of the solvent, and they need to be in grams and milliliters, and they already are, so that's good. And so when I do that math out, I get 0.0633 grams per milliliter. Now my path length is in 20 centimeters, and so I'm going to use that 1 decimeter is 10 centimeters. I'll take my 20 centimeters, all right, so now I think I have everything in the correct units. So my specific rotation will be the observed rotation divided by the concentration times the path length. And when I do that math out, I get negative 31.5. Okay, here's another example, this one involving calculating the enantiomeric excess. So the equation we have for the enantiomeric excess is given here, where we're going to use the observed rotation and the specific rotation for the pure enantiomer, and then multiply that by 100. So in this problem, because they're not giving us the concentrations and the path length, we're going to assume that we're using the standard concentration of 1 gram per milliliter and the standard path length of 1 decimeter. And so to get the percent EE, we just need to take the observed specific rotation of this sample divided by the specific rotation of the pure enantiomer and multiply by 100. So we get 92.4%. So the way to interpret what this value means is this means that 92.4%, or that we have 92.4% more of vitamin B7 than its enantiomer. And so I think the easy way to sort of break this number down is to assume that, okay, this is like saying we have 92.4% pure vitamin B7, and then the rest, the other 7.6%, is a mixture of the vitamin B7 and its enantiomer. So we've got 92.4% that's vitamin B7, and then 100 minus 92.4, we have 7.6% that's the mixture. And so this is a racemic mixture, right? And so half of this is going to be vitamin B7, and the other half is going to be the enantiomer. So when I divide that by 2, of that mixture, 3.8% is vitamin B7, and 3.8% is the enantiomer. So the total amount of the vitamin B7 is the excess plus half of the mixture. And so when I add those two together, I get 96.2% vitamin B7, and I get 3.8% is its enantiomer.